Hello students, in the series of lectures in the subject VLSI design, we are discussing semiconductor memories. In the previous lecture, we discussed static RAM. Now in this lecture, we will discuss dynamic RAM. Okay. So what are dynamic RAM? So dynamic RAM do not retain its state even if the power supply is on. Dynamic RAM is a kind of volatile memory. That is the right thing. But static RAM can retain its state when the power supply is on, but dynamic RAM cannot do this. It need to be refreshed at a periodic interval. Okay. So data, why it is so? Because data in this dynamic RAM is stored in the form of charge stored on a capacitor. Okay. And now we know that the charge leakage problem occurs when the when the capacitor is being charged. So due to that leakage of charge, okay, it cannot retain the data even if the supply is on. It need to be refreshed. Okay, so it require periodic refreshment, and it is less expensive than static RAM. It is less expensive than static RAM. So let us consider one transistor DRAM cell. So this is the simple one transistor 1T DRAM cell. Here we are using only one transistor, and one exclusive capacitor is used here. This is the word line, this is the bit line. Okay, so let us consider the read operation, or let us consider the write operation first. Okay, so if you want to write one in this, so in the bit line you will provide one signal here, and word line is one here will be given. So this transistor will be on, so this one level will go to this side. Okay, this will high voltage will appear here, so this capacitor will be charged, and this capacitor will be charged, and so it is analogous to the logic 1 writing. So this is how we can write logic 1 here in this. Okay, so how you will write a logic 0? Okay, so in order to write the logic 0, just you need to do just turn off the bit line. Okay, that is 0. Okay, so the word line would be 1. This is also 0. The capacitor will be discharged. Okay, now how to read? In order to read, let's say C is 1 here. Okay, or if you want to read, so you will have to select this word line equal to 1. So if you select this word line equal to 1, so this transistor will be on. So whatever voltage is at this capacitor, it will be shared with the data line. Okay, it will be shared with the data line. Okay, so this is this sense circuit will sense this voltage and will reflect the output accordingly. Now there is a mathematics in there. So let's say we have uh, one transistor DRAM cell like this. Okay, this is the capacitor C, and this is the word line, this is the bit line. Okay, bit line is also called as the data line. This is also called data line. So this can be also called as DL, data line. Okay, so let us consider the initial voltage of data line was VD. Okay, initial data line voltage was VD. So VD is equal to QD upon CD. Okay, and let us consider the initial cell voltage was VC. Means the initial capacitor, a voltage across the capacitor was, let's say, VC. So VC will be equal to QC upon CC. Okay. Now as the charge is shared between these two, so the final voltage at the data line will be total charge divided by the total capacitance, QD plus QC upon CD plus CC. Okay, when the data line is connected with the cell. Is it clear? So the total voltage, final voltage will be total charge. So here charge is QC, here charge is QD, here voltage is VD, here voltage is VC. So what will be the total final voltage at the data line? So total final voltage at the data line will be total charge divided by the total capacitance. So this is the voltage that we will get. Now what will be the voltage difference here? So voltage difference will be, initially voltage was VD, finally it was VF. So the difference between the voltages will be VD minus VF. Okay. So if you need to find this voltage difference, delta VD, so that will comes out after calculation. Just put the values here. So after calculation, that difference delta VD will come out to be like this. Okay. So uh, as you can see that this data line is connected to the arrays of so many transistors like this. Okay, so many cells are connected like this here. So obviously the capacitance of this data line will be much higher than this capacitance. Okay, so obviously CD will be very much greater than CC. Okay, so as CD is very much greater than CC, then what will happen? So the change in voltage will be approximately, as CD is very much greater than CC. So this change in voltage will be very low. Okay. And sense amplifier will have to detect this change. Okay. So this is one difficulty that comes in one transistor DRAM cell. Okay. Now this is 4T, 4 transistor DRAM cell. So in case of 4 transistor DRAM cell, this is these are the parasitic capacitances that you can see. So depending upon the charging and discharging of this parasitic capacitances, we interpret the stored data as 1 or 0. Okay. So the operation of this is pretty much simpler. I am not discussing that. So I will particularly discuss the 3 transistor diffusion, 3 transistor DRAM cell. And this is 3 transistor DRAM cell. I will discuss it in detail. Okay. So in 3 transistor DRAM cell, this is the structure of 3 transistor DRAM cell. Here you can see that this is the 3T DRAM cell. You can see it here. Okay. These are the 3 capacitors that you can see, C1, C2 and C3. So the voltage, whatever voltage that is here at C1, it signifies the logic 1 or 0 is stored in this cell. Okay. Now C2 signifies the capacitance associated with this column. C3 signifies the capacitance associated with this column. Okay. We have separate word lines for read and write operation. So for write operation, we have this word line. For read operation, we have this word line, RS. Okay. Again, we have separate data lines for read and write. Okay. So for input, we have this column. For output, we have this column. Okay. Now, at above of this, we have this pre-charge devices. So here we are connecting two NMOS transistors, MP1 and MP2, and these are connected to the supply voltage VDD. This is the PC, this is the pre-charge value that is given here. Okay. So this 3T RAM cell basically depends upon the two-phase non-overlapping clock screen. So first recharge event take place, then read or write operation will take place. So every read or write operation will be preceded by the pre-charge operation. And pre-charge operation is operated when PC value is 1. Okay, when PC value is 1, that will be pre-charge operation. Okay, how the pre-charge operation is performed, let's consider it. So this we have considered. When pre-charge PC is equal to 1, so pre-charge cycle, first of all let us consider the pre-charge cycle. So pre-charge cycle when PC is equal to 1, so here you can see when this PC will be 1, these two MP1 and MP2 NMOS transistors will be on. Okay, so when these two transistors are on, so supply is connected to both the columns. Okay, supply is connected to this column. Is it clear? Okay, so as the supply is connected to this column, this capacitor C2 will be charged up to the voltage equivalent to the logic high. So C2 will be charged up to the high logic level. Is it clear? Okay, so C2 will be the high logic level. Again, C3 will also charge up to the high logic level. Okay, so that's why this is called pre-charge phase. Okay, now let's say if we want uh, to write 1, so how we will do this? So if you want to write 1 here, so it should be preceded by the pre-charge stage. So as in pre-charge stage, it is clear uh, that C2 is analogous to logic high, C3 is analogous to logic high. These has been charged in the pre-charge stage. Now as PC goes down to 0, write operation or read operation can be performed. So if we want to write 1, okay, so we will give data 0, because if you will give data 0 here, then only 1 will pass here. Okay, so here you can see that so data will be 0. So if data will be 0 and inverted data is 0, okay, so what will happen? So this transistor MD transistor, this will be off because this is 0. So here is the disconnection that is formed. Okay, now you want to write something now. So if you want to write, so this word line will be selected as 1. So if this is 1, this transistor M1 will be on. So if this transistor M1 will be on, as we know C2 is already pre-charged to value 1. So this 1 will reflect here because this is a pass transistor. So accordingly, this capacitor C1 will be charged up to the voltage, let's say VDD. Okay. Now one question arises that there is a simultaneous path that has been created between C2 and C1. You can see it here because M1 has been replaced by the closed switch, and this is your capacitor C1. Okay, this is your capacitor C1. Now C2 is already charged up to the voltage VDD, let's say. This is charged up to the voltage VDD. Now the charge of C2 will be shared among C1 and C2. Okay, so initial charge will be equal to final charge. Now initially what was the charge? That was C2 multiplied by VDD Q equal to CV, and that will be equal to C2 multiplied by, let's say the voltage is VA. Okay, uh, at the nodes, let's say these voltages are VA, so C2 into VA plus that will be C1, yes, C1 into VA. So what will be the value of VA here? So the value of VA will come out to be C2 upon C1 plus C2 multiplied by VDD. As you know that the capacitor of this line, data line C2, is very much higher than C1. So if you put it here, VA will be approximately equal to VDD. Okay, so C1 will be charged up to voltage VDD, and that is analogous to the logic 1. So this is how you can write 1 in this uh, 3T DRAM cell. Okay, now let's say if you want to read the data from here. Okay, so if you want to read 1, means 1 has been stored here, you want to read it. Okay, so what you will done now, what you will done, followed by the write operation, that there will be a pre-charge stage also, because I have already told you that every read and write operation precedes with the pre-charge operation. Okay, so after the writing there will be pre-charge operation. Okay, so at the pre-charge operation, these C2 and C3 are again one logic high. Okay, now you want to read something now. Okay, so if you want to read from here, you will uh, on this RS signal. So this RS signal will be turned on. So when this RS signal will be turned on, read, this M3 transistor will be on. Okay, and remember, this is already charged up to voltage VDD. This is already charged up to voltage VDD. Now, as C1, as 1 is stored here, so this M2 is also on. So you can see that there is direct path for this C3 to discharge to this ground. Okay, so C3 will be discharged from 1 to 0. So this will be fully discharged. So this will be sensed by the sense amplifier that is connected to this line. Okay, and this discharging of the capacitor will be treated as logic 1. Okay, this is how you can read 1 in this case. Okay, so if the capacitor is discharging, then it interpret as 1. If it charges, then it interpret as 0. Okay, in read operation. So this is how you can read and write operation like this. And similarly, you can write 0 and 1 operation. In order to write 0, data bar should be 1. Okay, and the same process is continued. Okay, so this was all about